Hi, let's continue with 2.3, the dot product. The dot product and its procedures. In this section, we will develop an operation called the dot product, which allows us to calculate work in the case when the force vector and the motion vector have different directions. The dot product essentially tells us how much of the force vector is applied in the direction of the motion vector. The dot product can also help us measure the angle formed by a pair of vectors and the position of a vector relative to the coordinate axis. It even provides a simple test to determine whether two vectors meet at a right angle. All right, one of the major concepts in this section is the dot product. The dot product of vector u and vector v is given by the sum of the products of the components. So we're going to go ahead and multiply the matching component as if it were a coordinate point. So our x's, or that first number, being multiplied together, your y's, or that second number, being multiplied together, and your z's, that third component, being multiplied together, and then we follow by adding them. If this were a second dimension, then we'll only have two components. Think of it as an x and a y. It would work the same way, we just wouldn't have that third one. This may also be called a scalar product or the inner product. So if you see a problem asking what is the scalar product or what is the inner product, it's still asking you for the dot product. Let's do an example. Find the dot product of u and v. All right, let's go ahead and do this problem. So we begin by multiplying our first components. So 3 times -1 plus 5 times 3 plus 2 times 0. And then we add them up. So we get -3 plus 15 plus 0. We get 12 as our answer. I trust you can do B as well. B just has the vectors written as standard unit vectors, but if you don't like the way that's written, you can go ahead and change them to a vector. All right, I'll let you do B. Your answer should be 18. Moving forward, 2.3 properties of the dot product. So let U, V, and W be vectors, and let C be a scalar. So first we have the commutative property, which tells us that we can swap the order in multiplication. We have the distributive property, the associative property, and the property of magnitude. So let's go ahead and do example part A. Let vector A, vector B, and vector C find each of the following products. So A is asking us to multiply A times B and then C. Well, I've been totally incorrect by saying multiply. We're doing the dot product. Don't let that notation throw you off. So let's perform the dot product on A and B. So we'll multiply 1 times 0 plus 2 times 2 plus -3 times 4. This gives us 0, 4, and -12. And when we add them, we get -8. Lastly, we're going to multiply that into C. C is a vector. So we have -8 times 5, -1, and 3. This in return gives us -40, 8, and -24. Okay, I trust you can do B and C. Pretty straightforward. Using the dot product to find the angle between two vectors. When two non-zero vectors are placed in standard position, whether in 2 dimensions or 3 dimensions, they form an angle between them. The dot product provides a way to find the measure of the angle. Theorem 2.4. Evaluating a dot product. The dot product of two vectors is the product of magnitude of each vector and the cosine of angle between them. And our formula for that is the dot product of u and v is equal to the magnitude of u times the magnitude of v times cosine theta. Now remember, an equation is so powerful, we can use it however we'd like. A common way you'll see it is if you're being asked for the angle, you can solve for cosine theta, and that would just be the magnitude of u and v, not magnitude, the dot product of u and v, divided by the magnitude of u and the magnitude of v. So that's something else you can take from that equation. And we'll practice that in the next example. Find the measure of the angle between each of the vectors. All right, so for A, let me have the formula handy. For A, we have two sets of vector. They're written in standard unit vector form. So we have a vector 1, 1, 1, and 2, -1, -3. All right, so let's go ahead and work this out. I want to find the angle between them, so let's follow our formula. Cosine theta is equal to the dot product of u and v divided by the magnitude of those same vectors. Okay, so the dot product of u and v, that would be 1 times 2 plus 1 times -1 plus 1 times 3, and then the magnitude of each one. So it would be the square root of 1 squared plus 1 squared plus 1 squared times the square root of 2 squared plus -1 squared plus -3 squared. And that gives us 2 minus 1 plus 3 should be a -3. So that's a -3 divided by the square root of 3 times the square root of 14. All right. So in return, that gives us 2 minus 1 is 1, minus 3 is -2, divided by the square root of 14 times 3, 42. All right, so what are we trying to find? We're trying to find the angle between those two vectors. So we're almost there. What are we missing? We're missing the cosine from our formula. All we did was this part right here. So we're saying that cosine theta is equal to -2 divided by the square root of 42. All right, we want theta, so we apply cosine inverse. So that we have theta is equal to cosine inverse, or in your case, if you see arc cosine, that would be the same thing, of -2 over square root of 42. And that is our answer. If it wants a decimal, Then you would punch into your calculator. Just make sure you're careful whether they want degrees or radians. Don't forget about that. So let's talk about the measurements of the angles we may have. So when it's talking about these measurements, don't forget your trig unit circle where you have the point 1, 0, 0, 1, and -1, 0. And remember, x is always your cosine. So that's what it's talking about when it's talking about these limitations. Moving forward, the angle between two vectors can be acute when cosine theta is between 0 and 1. It can be obtuse when it's between -1 and 0, or straight when cosine theta equals -1. If cosine theta equals 1, then both vectors have the same direction. If cosine theta equals 0, then the vectors, when placed in the straight position, form a right angle. Theorem 2.5, orthogonal vectors. The non-zero vectors u and v are orthogonal vectors if and only if the dot product of u and v equals 0. When we say orthogonal, is that they meet at a right angle. Example, determine whether vector p and q are orthogonal vectors. So we're looking at these points where vector p has the points 1, 0, 5, and q has 10, 3, and -2. We want to perform the dot product, and what we're really doing is we're checking if our answer is 0. And that's all we really care for, since it just wants to know if they're orthogonal. All right, let's perform the dot product. 1 times 10, 0 times 3, plus 5 times -2. So we get 10 plus 0 minus 10. We get 0. Great. We can say, yes, they're orthogonal. Next example. Let V be 2, 3, 3. Find the measures of the angles formed by the following vectors. So V and I. So just in case this is weird, these vectors I, J, and K, those are the following vectors. So I would be 1, 0, 0. J would be 0, 1, 0. And vector K would be 0, 0, 1. Remember, they're just a standard unit vector. So I, J, and K represents the position. And since they're just themselves, they would just be 1. So I'll do A with you. I think you can do B and C on your own. So for A, we have vector B, which is 2, 3, and 3. And I, as a vector, would be 1, 0, 0. All right, we want to find the measure of the angle between them. So remember your formula. That would just be cosine theta is equal to the dot product of u and v divided by the magnitude of u and v. Okay, let's do that. So the dot product would be 2 times 1 plus 3 times 0 plus 3 times 0 divided by the square root of 2 squared plus 3 squared plus 3 squared plus the square root of 1 squared plus 0 squared plus 0 squared. And that gives us 2 plus 0 plus 0 divided by the square root of 22 and the square root of 1. So then we get 2 divided by the square root of 22. All right, we're applying that to cosine theta. And since we just want cosine, we take the arc cosine or the cosine inverse. So theta is equal to cosine inverse of 2 square root of 22. And if you punch it in your calculator, it should be about 1.30 radians. All right, that was A. Doing B and C are the same process, just slightly different vectors. Okay. The angle of a vector with each of the coordinate axes is called a direction angle. It's very important, practical in computations, and is essential in a field such as engineering. Definition: direction angles and direction cosines. The angles formed by a non-zero vector and the coordinate axes are called direction angles for a vector. Cosines for these angles are called the direction cosines. The last example would serve as an example of direction cosines. So what we did here, that is also direction cosines. So if you see a problem asking to find the direction cosine, it would be a special type of problem where you're trying to find the angle between two vectors, but one of the vectors is along the axis, just how I, j, and k were along the axis. Let's do an example. AA party supply, store, sells invitations, party favors, decorations, and food service items such as paper plates and napkins. Find when AA buys its inventory, it pays 25 cents per package of invitations and party favors. Decorations cost 50 cents, and food service items cost 20 cents. AAA sells invitations for $2.50 per package and party favors for $1.50 per package. Decorations sell for $4.50 each, and food service items for $1.25 per package. During the month of May, the party supply store sells 1,250 invitations, 342 party favors, 2,426 decorations, and 1,354 food service items. Use vectors and dot products to calculate how much money the party supply store sells during the month of May. How much does the store make in profit? Okay, so if we're going to use vectors, let's first stable or set up some structure. So if we're writing a vector, notice that everything was kind of kept in the same order. So it'd be easy to say invitations are the first component, then party favors, followed by decorations and food service. Okay, so it gives us three main pieces. It gives us cost, how much they sell for, and the quantity, how much they sell of each one. So let's make those vectors accordingly. So C for cost, the cost of each one, while invitations were 25 cents, party favors were 25 cents, decorations were 50 cents, and food service items were 20 cents per package. We also have how much they make, or how much they sold for. Let's make that P4, which will eventually develop into a profit. Invitations sold for $2.50. Party favors for $1.50. Decorations for $4.50. And food service for $1.25. All right, now we want to make a list of quantities of how much of each item was sold in May. So we have 1,258, 342, 2,426, and 1,354. All right, so just to remind you, C is cost, P is our price, and Q is our quantity. And we have these vectors to help us keep track of this information. Now our question is, how much did the store make in profit? That's what we want to find. Well, is there a way to first find out A, how much of material we have, and then B, find out how much we sold? Well, let's go ahead and do that. So let's first determine our sales. How much did we make? Sales. So we do that to find out how much we have made. We would take our price and our quantity and perform the dot product. So that would be 250 times 1,258. And this makes it easy to pair up, right? Because you know exactly where you're going to multiply each one by. Plus $1.50 times 342 plus 450 times 2,426 plus 1.25 times 1,354. We perform the dot product, get 3,145, 513, 10,917, and 1692.5. And we know that in sales we made 16,267.5. All right. Okay, now let's find how much we spent for all of this stuff. So let's do cost and quantity. All right, so this first one was P and Q. Let's go ahead and do this again, but with C and Q, the dot product of C and Q. So I won't drag you through all the work of the dot product. I know that's above you. We're just learning new language. So our answer for this, how much we spent on inventory, is 1,883.8. So can we figure out our profit? Yeah, we just subtract these two differences, right? So our answer would be, to find our profit, it would be the dot product of P and Q minus the dot product of C and Q. So that would give us a total of 14,383.7. So that's how we can use vectors to keep track of our how much profit we made. Direction, definition for vector projection. The vector projection of V onto U is the vector labeled projection of U and V. It has the same initial point as U and V and the same direction as U, and represents the components of V that acts on the direction of U. If theta represents the angle between U and V, then by properties of triangles, we know the length of the projection of U on V is the magnitude of the projection is equal to the magnitude of V times cosine theta, When expressing cosine theta in terms of the dot product, it becomes, so here we kind of break down and develop this formula. So we have that the projection is made up of magnitude of v times cosine theta. We know cosine theta is this right here, the dot product of u and v divided by the magnitude of u and v, by our previous formulas. Okay, and therefore, a little bit of algebra, we see our v's cancel. We can say that this is also true. So therefore, the projection of u and v is a dot product of u and v divided by the magnitude of u. We now multiply by unit vector in the direction of u to get the projection of u and v. So this just develops into another form of writing this same formula. So the projection of u and v is dot product of u and v divided by the magnitude of u squared times the magnitude of vector u. The length of this vector is also known as a scalar projection of v onto u, and it's denoted by the magnitude of projection of u and v is equal to the comp u and v, which is equal to the dot product of u and v divided by the magnitude of u. So here is an image of what we're trying to show. So we have a vector u and v, and we see what this new projection that we're talking about is made up. We see that right there. Find the projection of v onto u. All right, so we have a formula to follow. We learned this new formula, and it tells us that the projection of v onto v is equal to dot product of u and v divided by the magnitude of u squared times v times u. All right, let's go ahead and do A. Find the projection. So our numerator is made up by a dot product of those two vectors. So we have 3 times negative 1 plus 5 times 4 plus 1 times 3. And we divide it by the magnitude squared, which means we don't have to include the square root. The magnitude of u. So it would be negative 1, 4, negative 1 squared plus 4 squared plus 3 squared. And that will be multiplied by the vector of u, which is negative 1, 4, and 3. There we go. That's it. Let's go ahead and clean it up. In our numerator, we're left with negative 3 plus 20 plus 3 divided by 1 plus 16 plus 9 times the vector of negative 1, 4, and 3. And so we're left with 20 over 26 times the vector of negative 1, 4, and 3. And of course, you would have to clean up that fraction. So that would be 10 over 13 times the vector. Once we multiply it in, our answer would be negative 10 over 13, 40 over 13, and 30 over 13. I trust you can go ahead and do B on your own. All of these questions are straight from your textbook, so if you want to actually see B, just see your text. You can see it done. All right. Sometimes it is useful to decompose vectors, so to break it down. That is, to break a vector apart into a sum. This process is called the resolution of a vector into components. Projections allow us to identify two orthogonal vectors having a desired sum. To do this, first we find the projection, then find the difference of the projection and the vector. This will produce your two desired vectors. So what we're saying is we can also go ahead and take our projection that we learned, and we can use that to develop this to break down vectors. So let's say a vector we're working with, we want to break it down to two different vectors. We can do that too. Because remember, you can add vectors, right? We have a vector plus another vector, and that also forms a magnitude with distance. Example, express V, which is 8, -3, -3, as a sum of orthogonal vectors such that one of the vectors has the same direction of u, 2, 3, 2. All right, so what we're trying to do is we're trying to break down this vector as two vectors. Keep in mind the direction of u. Okay, well, if we read above, it tells us just how to do it. We're going to find the projection and then find the difference of the vector projection from the vector. So let's start off by finding the projection. So we have our projection P is equal to the projection of u onto V, which is the dot product of u and V divided by the magnitude of u squared times the vector V. All right. So the dot product, we have 8 times 2 plus -3 times 3 plus -3 times 2 divided by u, we have 2 squared plus 3 squared plus 2 squared, and then our vector u. So this gives us 1/17. And then our vector u is 2, 3, 2. So in our new vector that we just created, P is equal to 2/17, 3/17, and 2/17. Okay, now we want to work with vector P to find the difference, to find the other vector, which would be a result from a vector sum. So what we want to do is take Q from V minus P. What is Q? Q is our new vector that we're trying to find. So we found P. Now we're trying to create another vector Q. That'll be made up by V minus P. So we have V here, and we have this vector P that we found. Let's go ahead and work that out. So V is 8, -3, -3, minus P, which is 2/17, 3/17, and 2/17. Okay, we find the difference, and that gives us 134/17, -54/17, and -53/17. That is our new vector Q. All right, so this is a very loaded question. We now have two vectors that represent V. We have P and Q give us V. But it wants us to check that it's orthogonal. So to do so, another extra piece we gotta do, and I'll let you do this on your own. So take a moment, pause the video, and show the dot product of P and Q is equal to 0, or 1. Do we want 0 or 1? Orthogonal, I think I have a typo in my notes. We have orthogonal when it is equal to 0. Yeah, I wrote 1 in my notes. So we want to make sure it's 0, which you should have. And then we have reached our answer. We have two vectors that equal b. So then b is equal to p plus q. You can go ahead and check it. Take your vector p, add it to your vector q, and you'll see they'll add up to your initial vector b. And in case you're thrown off by the instruction, these are the steps. You first want to find the projection. Take the difference from the projection to your vector, and this will give you your two vectors, p and q. Next example. A container ship leaves port traveling 50 degrees northeast. Its engine generates a speed of 20 knots along the path. In addition, the ocean current moves the ship northeast at a speed of 2 knots. Considering both the engine and the current, how fast is the ship moving in the direction 50 degrees northeast? Round your answer to the nearest 2 decimal places. Okay, so to begin, let v be the velocity. The velocity vector generated by the engine, and let w be the velocity. The velocity vector of the current. We already know that the magnitude of v is equal to 20 along the desired route. We just need to add the scalar projection of w onto v. All right, so to find this answer, we're going to go ahead and take the dot product of v and w divided by the magnitude of v. And we're taking our definition above and we're working with that formula so that we can work with what we have. So all these formulas here we're gonna rework them so that we can work with what we have. What do we have? We have degree 30 and we have this v. So we're going to go ahead, let me erase all those markings. We're going to work up our formula. We're here. We can work up our formula so that we can work with this one. They're essentially equal since we worked our way down using the triangle property to come up with the same result. So we jump to the current page. We can go ahead and steal from our formulas above to have the magnitude of v equals the cosine theta for our formula. So I have magnitude of v times cosine of 30, which is this angle right here. So our magnitude v, I said 20, it's 2. So we have 2 times cosine of 30 using our unit circle or your calculator or your memory from your trig class. We get our answer is square root of 3, which is about 1.73 knots. We add that to the 20 of our initial knots, and we can say the ship is adding or sailing 21.73 knots, 15 degrees northeast. That's where we got the 21. 1.73 plus 20. Okay, moving forward. Now that we understand dot products, we can see how to apply them in real-life situations. The most common application of the dot product of two vectors is the equation of work. From physics, we know that work is done by when an object is moved by force. When the force is constant and applied in the same direction of the object moves, then we define the work done as the product of the force and the distance of the object travels. So F equals F times D. So we have a new definition. When the constant force is applied to an object, so the force moves in a straight line from point P to Q, when the work W done by force F is acting on angle theta from the line of motion is given by W equals F times the dot or F dot product P of Q, or the magnitude of F times the magnitude of PQ times cosine theta. So really this is two formulas in one. We can have F dot product of P and Q, which is a vector from 2 points, or we can work with magnitudes. The magnitude of F times the magnitude of PQ times cosine theta. Let's do an example. Let's do an example together. So all the work, all the thought process is there. Let's consider a problem of a child pulling a wagon. Suppose a child is pulling a wagon with a force given a magnitude of 8 pounds on the handle at an angle of 55 degrees. If the child pulls the wagon 50 feet, find the work done by force. Okay, so we're given an angle, we're given a magnitude, and we're also given a distance. So we have our formula. Thus we have W equals magnitude of F, the magnitude of Q, PQ, and cosine theta. We go ahead and input those values, multiply them, and our answer is 229 feet per pound. One small note. In the US, the standard unit we measure the magnitude of force, F, in pounds. The magnitude of displacement vector PQ tells us how far an object moves, and it's measured in feet. The customary unit of measure for work, then, is foot to pound. 1 foot-pound is the amount of work required to move an object weighing 1 pound a distance of 1 foot straight up. In the metric system, the unit measure for force is the Newton, and the unit measure for magnitude for work is the Newton meter, Nm, or joule. So when you work with these problems, you can also add, instead of adding foot per pound, you can say joule or newtons per meter. All right, let's do an example. And these aren't so bad, right? We have a formula. You can have one or two ways. So we saw an example with the one we did together, deals with how a setup might look with that first equation. And you know you're going to have that equation where you're given a degree measurement. You're going to be given a force, a distance, and a weight. I'm sorry, and a degree. Now, the other one would be a force and a distance, maybe from point A to point B, or it might straight up give you a vector, which would be ideal since you are performing the dot product, right? I know as mathematicians, we're so used to seeing that little dot as a multiplication, but for this class, you really have to rearrange your brain and think, oh, okay, that means dot product. Let's do an example. A conveyor belt generates a force. All right, we have F, force, cool, of 5i minus 3j plus k, and it moves the suitcase from point 111 to point 947 along a straight line. Find the work done by the conveyor belt. The distance is measured in meters and the force is measured in newtons. Okay, so we know how we're going to write at the end, but most importantly, we can already pick out which form we're going to use. We weren't given any degrees, right? So we know we're going to use that W equals F dot product of PQ. So we have our formula. W is equal F PQ. Now, don't let PQ throw you off. Remember, you need to find that as a vector. So let's take our points. We have PQ as, let's write it as a vector. To refer back to 2.1, you have to find the difference of each of the coordinates to find your vector. So that means we're going to take 9 minus 1, 7 minus 1, 4 minus 1, and then 7 minus 1. So we're taking our 2 points and we're finding their difference so we can create a vector to which we can do dot product on. So our vector, PQ as a vector, would be 8, 3, 6. Once we subtract, or if you want to write it in standard unit vector, that would be 8i plus 3j plus 6k. However it's interpreted, or however we write it, we know how to interpret it. Okay, let's go ahead and do our problem. F is equal to the dot product of F and PQ. So we're going to perform the dot product on 5, negative 3, 1, and 8, 3, and 6. So it gives us 8 times 5 plus 3 times negative 3 and 1 times 6. That gives us 37, and it wants it in newtons. So, or we can write it as joules too, a J for joules. All right, you can write the answer either way. That's it for section 2.3. Some highlights. Make sure you look over dot product. Dot product is going to give you just a single answer in return. We also talked about projections. Projections help us work with two vectors and it can essentially help us break down a vector because it's helping you find an extra component of it. And we also worked with work, which is this last two examples we did. All right. Thank you.